Okay, I believe we are recording and we should be good to go. All right, so are there any questions on anything at this point? I know some people said they had some questions on the homework, but I wanted to check to see if you had any questions on anything so far.
I would appreciate going over the homework assignment 4 that we just turned in. I think that'd be a good review because that topic will be on the exam, correct?
Yep. Somebody mute their, sounds like somebody is doing a, so I'm not sure why it's because I'm sharing my screen. Can you all see, let me bring this up, did you explain everything at this point? Yes, okay. All right, so do you want to do any specific questions or just go through problems 1 and kind of proceed from there?
Yeah.
All right, so problem number 1, which says we have a 3-phase 13.2 kV 50 MVA Y-connected sync generator, has an armature reactance of 2.19 ohms per phase and a leakage reactance of 0.3 ohms per phase. So the first thing we can do is we can start to draw our equivalent circuit. And we have our armature reactance, J2.1, and our leakage reactance of J0.3 ohms. And then this is the terminal voltage. Now it doesn't tell us if we have any information in terms of, you know, if it's Y or delta. So generally speaking, generators are going to be configured in a Y because the neutral connection allows you to, you know, put some sort of impedance device in the neutral to monitor and control the amount of ground fault current. And you'll learn more about that if you take some relaying stuff that we've been working on. But essentially what you have is a voltage here, whoops, wrong side, of 13.2 kV at an angle of 0, right? That's the nominal voltage because this is the terminal. This is what you actually have access to. This EA is based on whatever value it needs to be. So it'll give you that specific value to go ahead and drive that. So now it says it's delivering full load current at rated voltage and a 0.8 power factor. So the first thing is, what is IFLA? Do you know how to solve for IFLA? Anybody can answer the question. If you don't know, that's okay too. All right, so what's the rating of the generator?
So are you just saying to take like the 50 and divide it by the phase voltage, so like the square root of 3 times the 13.2K?
There's a couple ways to do that, right? That's S3 phase is 50 MVA. You can either do it, like you said, as a 3-phase quantity, or you can do it as a single-phase quantity. It's going to give you the same result, the square root of 3 there. So we have S3 phase is 50 MVA, or S single phase is 50 MVA divided by 3, right? Because unless it's a phasor, everything is going to be multiplied or divided by 3. So my full load amps is going to be, and again, I can either use a 13.2 or this or the other value, but I'm always going to use S equals VI conjugate. So let's use our equation because this is the one you're going to be most commonly using when you get out of industry because it makes it a lot easier. You don't have to keep track of quantities and use the square root of 3 there. So if I have my IFLA here, I'm going to take my S3 phase value and divide it by square root of 3 times V line, and I'm going to take the conjugate of that term. Okay? So now I have 50 MVA divided by square root of 3 times 13.2 kV. And the question is, what is the angle going to be? Well, I know it's a 0.8 lagging power factor. So I can just put the inverse cosine of 0.8. And as long as I have my negative there, I know that my current lags my voltage because I've specified my angle to be 0 there, right? So my full load amps at a 0.8 power factor gives me that specific value. Do I need to actually calculate what the full load amps are, or do you feel like you all can do that?
I'm all set there, Paul.
Okay. So that's my full load amps, which is part B, right? You've already gone ahead and done part B to give you the full load, the rated load current. And we did it at a 0.8 power factor, but essentially all the full load current is going to do is change the magnitude. And since we've expressed it as a magnitude, it doesn't change whether it's a 0.8 power factor, a 0.9 power factor, or unity. It's still going to be rated for that specific value. So if we do things in terms of magnitude, we're good to go. So part A, synchronous reactance is just going to be equal to XS, which is going to be equal to 2.19 plus 0.3. That's just the sum of the armature reactance and the leakage reactance. Oops. Sorry about that. Now the question is, what is the air gap voltage? Does anybody know or understand what the air gap voltage is?
Would you take your do a sum of the voltages, but you'd look at just the current through the point 3, like through the imaginary, the 0.3, like the inductance piece of it?
Correct. Yep. So you have an armature reaction and a 0.3, and actually this would be better to be drawn over here. So let's erase that, and let's put that in the right spot to make it easier to see. So we have J2.19 and J.3. So my air gap voltage is the voltage that I'm going to be seeing at that point, which means I've got my terminal voltage here. Then I include the voltage drop that I have here. So EAG is going to be equal to 13.2K divided by square root of 3. What's the voltage drop across that J 2.19 ohm resistor? It's the current through it times J 2.19. That current goes there. That's the current value that you're going to be using. And that gives
wait, I'm now confused. Why did we do it across the 2.19? I thought it was across the 0.3.
Well, that would just be the voltage drop here, right? Let me see if I can bring up the image. Hold on, because I'm using two computers. It gets a little bit. Let's see if I can find the figure. Do it that way. Okay. Let's see if I can share. So I have to stop sharing with this screen. So bear with me as I get to this one.
I guess my question is, Paul, between because I know there's the air gap voltage and the internal generated voltage.
Yep.
And so what you're saying is the air gap voltage is the voltage drop across the armature reactance?
No, it's not a voltage drop across anything, right? You have to include the voltage drop that's associated with a terminal. So you've got a terminal voltage that has a voltage drop of 13.2 divided by square root of 3. Then I have to add to that the voltage drop across the leakage reactance, and that is going to give me my air gap voltage. Okay?
Okay.
Let me bring up this screen here. And share my screen. Okay, can you all see my screen? So the voltage I'm
Yes.
talking about is here. So it's not this voltage drop here, it is here.
Okay.
The voltage that I'm talking about. So it's this individual voltage drop. Oh. You can also see, well, it doesn't actually say in this image here. No, that voltage there. So essentially it's the voltage that would be traveling across the air gap to give you that specific value. And that's why,
Okay. That's why we don't use the reactance of the leakage. We use the reactance of the armatures because you're looking at it across the terminals.
Right. Yep.
Okay.
All right, let's see if I can share the screen back here. It's very awkward to do two computers at once and figure out where you are. Okay. So that's what we're talking about there for that problem. Now
and then to find the internal generated voltage, it'd be the opposite of that, where you'd use I times J.3, because it'd be the opposite voltage terminal.
Nope. So if I go back to the original circuit, because I don't have it here, if I draw my equivalent circuit, I've got, where did I get the, I thought I drew it on this one, I guess I did not. If I draw my equivalent circuit again, this is the internal generated voltage that I have, the EA there. And I have to include all these voltage drops to get to EA. So I always have to include that VT.
Okay, so it's going to be between, I understand. Yep, but never mind, I'm good.
Okay.
Thank you.
Yep, sure. So it's E air gap plus my voltage drop I times J.3. So it should always be above whatever the terminal voltage is, except if we have reactive power going into the machine. So if it's an underexcited machine, then we actually have some of the magnetic energy that's required here is going to be supplied by the line, and that's why that value would be reduced. So E, voltage regulation, that's a percent VR, is V no load minus V full load over V full load times 100%. And so the question is, what is V full load? Well, V full load is this voltage here, right? That's what you're actually doing the nominal voltage to control to. So your V full load voltage is that value. Your no load voltage is if the current through your circuit, I, goes to 0, then what does the voltage on the terminal become? It becomes EA. So your V no load is just your EA. And essentially the reason being that is the value is, remember what determines what my EA is. EA is equal to K times phi times omega. So that's when we had those curves. This is our field current, and we had something that does this. That is the EA. So it's interesting, but the actual armature voltage that you have is really just determined by my field current. So when you talk about operation of the grid, you can just control the amount of field current, and that'll either increase or decrease the excitation to the point where you can change your power factor on your generating unit. And it's all based on just controlling the magnitude of that voltage. The power, though, remember that has as a function of the torque angle, and that's when you have to increase or decrease the torque angle, which means you have to slightly speed up or slightly slow it down for a brief instance in time. The generator, which means you have to increase or decrease the amount of steam or fuel that goes into your reciprocating engine to get it to speed up or slow down at a period of time. So I said that that was E, that should actually be F. So let's make that F. And then E, what's the power angle? Is there a different term that we use? It is delta, right? It's the torque angle. So when you calculate EA, you have a magnitude, you also have an angle. So the angle that you get in this part D here is the power angle. Okay? And you can always check your work, because if it's a generator, do you recall what the power angle needs to be? It's a positive number, right? If it's a motor, it's a negative number. And that was all based on our phasor diagram. Here's a terminal voltage. Here is EA if it's a generator. And here is EA if it's a motor. So it only has to do with whether delta is positive or negative. If it's a positive number, it's a generator. If it's a negative number, it's a motor. And then we also added on to that the magnitudes. So if it's greater magnitude than UT, then it supplies reactive power, right? It supplies Q. If it's less than, and I'm going to just draw it up here, it absorbs Q. So you can just look at a phasor diagram, and it's especially for generators, because generators have very large X over R ratios. And that's another thing which makes generator protection really challenging, because you have so much fault current available for you that is not symmetrical. And we'll discuss that more probably next year. You have so much fault current that's asymmetrical, you have to have special breakers, generator circuit breakers, that can interrupt that. So I will pause and see if there are any questions on this one. Intentionally not going fast. Come on, somebody's gonna have to have a question. Okay, if you're sure, I can continue on to the next problem. Problem number 2. So let's kind of read this one together and see if we can reference, what the highlighted or what the important information is. We have a 3-phase, 480 volt, 2-pole, delta connected synchronous generator. Is any of that stuff relevant for any of these calculations here? Amount of field current, efficiency, terminal voltage, field current, terminal voltage. Is any of that reliant on the number of poles?
No.
Yeah, what does the pole or the number of poles ultimately determine for a synchronous generator? It's just going to tell you the speed, right? All it tells you is the speed of operation. So it doesn't have any, it's not important from a perspective of anything other than it just tells you what the speed is. So if we start looking at problems where we're trying to do speed, it becomes a much bigger issue for us to figure out what's exactly going on. But since we don't really care too much about the speed on this particular problem, it's not asked for us, we don't necessarily need to worry about that. So we're not worrying about that. The 480 volts is useful to tell us what the rating is, but other than knowing that it's 480 volt, it doesn't really tell us anything other than, okay, what the nominal voltage is. And because we have the curve that's shown, we don't really need to know more information, because that curve is going to tell us pretty much everything we need. I called it a delta connected generator, and the reason why I said that is because if you look at the curve that we have, which is field current versus voltage, well, I didn't say if that's a phase voltage or a line voltage. What I did is, because it's a delta, phase and line voltage are exactly the same. So we don't even care necessarily what's going on with that. So the delta connected only tells us that the phase voltage is the same as the line voltage, but whether it's 480 volt or 2-pole, we have the curve, it doesn't matter. Now, all these other parameters are pretty important for us to figure out the sufficiency of the generator, because RA is going to give us some losses inside the machine, right? So the RA is going to tell us how much the efficiency is going to be and go from there. The excess does not affect efficiency because that doesn't consume any power. But what it does do is it consumes reactive power, depending on the power factor. So at that point, what we say is that's going to affect our voltage magnitude. So it's going to affect our armature voltage and go from there. So what we're going to do is use this curve to figure out exactly what's happening. So let's see if I can bring up the curve on this one. Hopefully this will work. Let's see. I don't see assignment 4 here, so just bear with me while I bring up assignment 4. I will upload it to the folder and I can see it. And I apologize, I'm working out of the house because we've sort of been kicked off campus. So my internet is not particularly fast. So see, there you are. Okay. Copy that there. Now I should be able to go into here and download that. Oops. Okay. Can you all see the plot there? Is it reasonably good quality that you can see what's happening?
Yes.
Yeah.
Okay. You also can work with it. So the first question it asks you, so I'm going to go back up and down here, and I apologize for that. The amount of field current for the rated voltage at no load. So as I mentioned, you have a curve that shows you open circuit characteristics as well as the air gap line, correct? Well, generators, real world generators today are operated under saturated conditions. So this open circuit characteristic is actually showing you what the terminal voltage is going to be when you have no load. So to answer the problem for number 1, which is the amount of field current at no load for 480 volts, all I need to do is read off the curve where I'm getting approximately 480. So let's zoom in just a little bit more. And again, I apologize, the quality of this is not great, but let's say that it's about here. So this is my 480 volt point. And I run across that line, and I don't stop at the air gap. I go all the way to my open circuit characteristic, which is what the actual voltage is going to be under these open circuit conditions. And then if I draw down, I need around 4.5 amps or so of field current to give me my 480 volts of terminal voltage under those conditions. So at that point, it's just looking at the saturation characteristics for the curve, reading it off the curve, and making a determination is this sufficient for us? Okay. Any questions on that? All right, so now the question is, the field current required for 480 volts, when the load current is 1,000 amps at a 0.85 power factor. So at this point, we can't use that curve because we don't have a condition where it's an open circuit characteristics. However, what we can do is draw our equivalent circuit. This is 0.01. This is J.12. Our terminal voltage here is 480 at an angle of 0 because it's delta connected. Now, all we need are the voltage drops across those elements to calculate what EA needs to be to deliver that. How do I get the voltage drops across those elements? Do you all recall? We just discussed it in the previous problem. All right.
You're going to do the voltage, and then you're going to add to it the current times each of the two reactances.
Exactly. So it's I times the 0.01 plus J 0.12. So all I need at this point is I. Is there a way to calculate what I is? Well, I told you what the current is. It's 1,000 amps. That's magnitude only, right? How do I get the angle of that?
You would just do the inverse
cosine.
Yeah.
Of 0.85. And it's lagging, so that means I put I here. So that is my current. That should give you my EA.
I have a question.
Sure.
Do we divide, because it's delta the current, by the square root of 3?
Well, you could. It just depends on what you're measuring or what you're monitoring. So if the load current is, let me go up over here. So if the load current is going to, so if this is the terminal and I've got two other phases here. So let's say I've got another phase here and here. Then yes, I would divide that by the square root of 3 to do that. But if I'm looking at it at each individual winding, that would be the case. So your best bet is to divide that by the square root of 3.
So we should for this problem.
Yes. Because it's load current, so my generator is sitting here, and all I have is 3 wires. So that when I talk about load current, I talk about the 1,000 amps here. But what actually is traveling in one of the phases, right, because this is delta connected, which means I've got, the 3 connected sort of this way, and this way. Sorry for the ugly figure. But that current here is going to divide amongst the 2 units because I've got 2 connections two connections going to each line. So if I draw it this way, maybe you can see it a little bit better. You can see that I have some current going here and some current going in here. So that's why I have to divide that by square root of 3. So yes. And to check your work, I got about 524 volts is what was needed to do that. That's the EA. So the question now is how much current do I need, field current do I need? Now I have to go back over here and look where I get about 524. So let's say that it's approximately here. And again, this is ballpark because the quality of the figure is not great. And then I just try to draw a straight line as possible and drop down. So what is that, 5.7 amps or so of field current to deliver 1,000 amps to the load at that 0.85 power factor. Questions on that one? That one you needed to do 2 things, right? You needed to actually solve for the 500, we'll just call it 525 volts there. And then you could pull the field current from that. Questions? Okay. How do you calculate efficiency? What's the general equation for efficiency?
P out over P in.
Yeah, very good. P out over P in. What's P out?
When you have to calculate it
Yep.
by 3 times V phase times I times cosine theta.
Yep.
Or is that wrong? Oh,
No,
okay.
no, you're absolutely correct. It would actually, it's easier to just always use that square root of 3 because you have some line and phase currents. Remember, this current here is a line current. So if you divide it by square root of 3, as Annalise, I think, had correctly said, then that would be a phase current. But if you're going to use the 1,000 amps, you use a line current. So generally, I just try to do everything in terms of the line quantities. So I get square root of 3 times 480 times 1,000. And then you multiply by the cosine of theta. What is the cosine of theta in this case?
0.8.
0.85.
Oh,
right?
0.85.
Yep. And that's the power to the utility, right? The interconnection. That's P out. How do you calculate P in? I'll give you a clue. It starts with P out.
When you
Yeah.
add the other like line losses to it,
Line losses,
or power losses, I mean. Oops.
other power losses, yes. So it's P out. What are the power losses here? Do you have the description of the problem? Does it give you any losses in there?
30K and 20K watts.
So you've got plus 30K, plus 20K. Any other losses?
I'm
Those are
unsure.
the only two listed, right?
Those are the only two listed in the problem, but are those the only losses? Go back to your equivalent circuit. Isn't this a resistor? Doesn't that have I squared R losses with it?
Mhm.
So I'm going to include the winding losses because I've got current flow through my windings, which means I'm going to have some losses there. So I have to add to it I, right, times squared times R, which is 0.01. Is this value the 1,000 amps or 1,000 amps divided by square root of 3? Because you have got the current going through that 0.01 ohm load or 0.01 equivalent armature resistance, it's going to be the current actually through each phase. So it's going to be the 1,000 amps divided by square root of 3, and I square that entire term. But it doesn't even matter because remember there are 3 phases, so I have to multiply that by 3 to make sure that I get my total losses. So the square root of 3's actually will cancel, the squared will actually cancel out with the 3, but that's how I get that value. And that is P in. So the efficiency now is just the P out over the P in. Questions on that? Does that make sense when you draw it that way? If you get confused, you can always draw your P in and P out and start showing your losses, right? My P in is the mechanical power, so I've got to start taking out some mechanical losses because of the rotation. So I'm going to take out my 30 kilowatts because that's rotational losses. Now I'm going to go into the core. So I'm going to take out my 20 kilowatts here. And then the last thing I do is I'm going to take out my armature copper losses. And that's that 3 I squared R. And that's where I get the efficiency. What's the terminal voltage if the load is suddenly disconnected? What does a terminal voltage go to?
Would it be 480?
Well, the question is, did I adjust the field current here? If the load is suddenly disconnected, have I changed this at all?
No, so it'd still be the 524, right?
524, yep, or 525, exactly. Because the field current hasn't had a chance to adjust, it stays as 525 or 524. So that's what the no load voltage becomes, even though my terminal voltage, you know, I'm trying to say it's fixed at 480 volts. I haven't adjusted the field voltage. So if I'm just connecting a generator to a single load where there's no other generation, it bumps up almost immediately to 525. Do we need to do part E, or is that somewhat self-explanatory?
I'm all set on part E.
Okay.
Could we go over it actually?
Sure. The only thing for part E, and are you all still seeing my screen? I'm having some problems toggling back and forth.
Yeah, we can still see it, Paul.
Okay. So the difference now, everything is going to stay the same. It becomes EA equals your R plus JX times 1,000 divided by square root of 3. What's the angle become now? What's the difference in angle? What has shifted in the problem description when we did our first current to this current? Take a look at the previous part and what do you see for a difference?
Went from lagging to leading.
Yep. So you were lagging, you are now leading. How does that impact anything, if at all? What's the
You
thing
won't
that
have
it
the
impacts?
negative sign.
Yeah, the current angle is no longer a negative inverse cosine of 0.85. It becomes, let me highlight this with a different color, a positive number. That's the only thing that changes. And if you do that, what's interesting is that the voltage, and I'm only going to give you the magnitude of voltage because it's only really what's important to us, is we get 453 volts magnitude. So why is that interesting? Because remember how we talked about overexcited, underexcited? If it's a leading power factor, that means, here's my generator, that means Q is going into the generator. So that means that the magnetic field that's required to energize the XS is partially being supplied from whatever it's connected to. So there might be some synchronous machines that are there that are not able to control the voltage but can export some reactive power. So the voltage then becomes 453. So it's lower. Exactly what we said when we did our phasor diagram discussion previously. And that works pretty well. And I think, unless I'm missing some, that was it for that problem, those problems.
Would you not add 480 to it, or?
Oh, yes, yep. I'm sorry. Got to add 480. That's only the voltage drop. Thank you. So I got to add. Sorry about that. Okay. Any other question on the assignment? How does the idea of a test on Thursday sound? Thumbs up, thumbs down?
I'd vote for next week.
Okay. Next Tuesday?
I mean,
Perfect.
I have a question. So what is going to be the general format for this exam? Like, is it going to be just like your other exams, except now we're doing it at home and we'll have like, we click on and we have an hour to do it? Or is it going to be longer? Are you going to have more questions?
Sure. Great questions. So here's what I'm thinking. And again, I'm happy to, to sort of collaborate and figure out what makes sense in terms of what you all think of. Here's my thought is the test will be, it's going to be open book, open note, obviously. And what we're going to do is I'll make the test available on whatever day we decide we want it to be available. You'll have that day to do the exam. So you'll have, I'll make it available at midnight if anybody wants to start it at midnight, and then you'll have till the following midnight to complete it. I'll give you a total of 3 hours to do the test, but I'll write it again as if you're doing the test. You would only need an hour to do it perhaps. And then you'll have that 3 hour window. So once you start the test, you have to submit your completed test within a 3 hour time frame. If you don't, it'll close and you won't have a submission. So basically it's like, I'm walking out of the room with your exam. If you don't hand it in to me, then you don't get a grade for the test. So you'll do the test on paper, whatever you need. You'll have your resources, your computer, your notes, whatever, calculator, MATLAB, whatever you want to use. But you don't have friends to do it. This is just testing your own knowledge and ability. And then after 3 hours, you don't have to scan it. Does anybody not have a cell phone? If you don't feel comfortable answering, you can just privately message me. But most people have cell phones, and all you need to do is take a photo of your exam. So take, however many pages you have, just take that many photos. And then you just have to add that as a zip file. So put it into a zip file, and then I'll make available when you enter the test, you'll upload a file, which is a zip file containing the however many pages of the photo of the exam that you have. So it'll be same thing. It'll be, you'll have a chance to get partial credit on the test, and we'll go from there. That's what I think would be a fair way to do it, but I'm open to suggestion if that doesn't sound like a good way to do it.
No, that sounds fabulous.
If that works.
So Paul,
Yes.
would it be okay if we put it in like a single PDF document when we turn it in, or do you want it in a zip file?
No, you can do a single PDF. I was
okay.
just doing it as a zip file because some of you all don't have the Adobe Pro, so you don't have the ability to do that. If you want to combine them into a single file, like if you have a scanner, most people can do a scan and it can scan to one PDF, but not everybody has a scanner capability. But most of you all have a cell phone that can do photos, and then as long as you have those photos sent to your email, then you'll have the files in an email. You can just upload them, and I'll actually extend it to 3.5 hours, so I'll give you an additional half hour to deal with logistics of uploading, combining the tests. I'm assuming half an hour should be enough time to do that. Does anybody think that would take more than half an hour? Okay, so if that's not the case, then that should be fine. So the question then is, if that seems like a fair approach, what about the exam? Do you want it this Thursday? Do you want it the following Tuesday? And then if we don't do it this Thursday, what would you like to do for a class on Thursday? Do you want to continue on with the discussion of induction motors, or do you want to do another, quote unquote, closer review session to go over some of these things? I'm not exactly sure, what's happening with that, but that would be helpful.
Right now, the exam is going to be on chapter 3 and 4, correct?
Correct.
And so that's on like AC machinery and synchronous motors.
Going to be synchronous motors and generators, right? Because the only difference is the current direction, but its
Right,
operation is essentially the same. It just depends on which direction the power is going. So synchronous motors, generators, which is chapter 4, and then rotating AC waveforms, which was chapter 3. I did get a chat from somebody that said, oh, no, that was to everyone. So, okay. Thank you, Annalise.
Yeah.
If it's difficult for anybody, you're welcome to just take pictures and then send me images. You have to combine them into one file, though, because if you try to do individual files, it won't allow you to do that. You'll only get one file solution, and then it'll be a little bit difficult. I encourage you, if you don't submit it that way, and you try to email me, then the timing is not going to work because I have no idea when you started the test. So that's why it's important for you to upload your information there. The other thing I would say is just make sure you have really good internet access, because if you get kicked off, then the test will auto submit. So if you close out of it, the timer still times. It doesn't stop. So, and then you can't get back in. So it makes it really difficult. So the question on the table is, when do we do the test? Do we want it this Thursday, or do we want it next week?
Tuesday.
Pardon?
It doesn't
Tuesday.
matter.
I hear it doesn't matter. I hear a Tuesday.
I can do next Tuesday.
Sorry?
I do next Tuesday.
Next Tuesday. So I got 2 for next Tuesday. 1, it doesn't matter. Anybody for this Thursday? Okay. So we'll do it next Tuesday then. Do you want to do a live class this coming Thursday, to do recitation type things or any specific questions, or?
I think a live question recitation would be really awesome.
Yeah, recitation will definitely.
Do we want to try to do it at 10 o'clock as usual, or do we prefer to do it at 2 when the class is supposed to be live?
I can do either.
2 o'clock would work better for me, I think.
Okay.
Yeah, cool.
We can do 2. I can set that up. That's not a problem. All right, well, if there are no other questions, I will end the meeting, and I will see you all Thursday at 2 p.m. with any questions you may have. Thank you very much.
Thank you, Paul. You have a good day.